So let's pick up where we left off. Right here's where we left off at the additive interval property. So first of all, you have to know that your limits A and B, there's another limit C that's in between A and B. So that's what this is up there. All right. So if you know, I'm going to talk about the right side first. If you know that the when you add from A to C, so right here, plus C to B, then that equals the overall limit A to B. So it would look something like this. So here's our graph. Here's A, here's B, and then C is somewhere in between. So if you add up, it says from A to C, and if you add this area right here, and then C to B, this area right here, that's the same as the area from all the way from A to B. That's what that's saying. So it's pretty straightforward, common sense, but it has to be said. It's just one of those things you have to say. All right, and then down here we've been playing around with some of these ideas a little bit already, but again, this is just saying what needs to be said. If you are integrating and there's a constant being multiplied to your function, you can take that constant out front like this, and then just focus in on integrating that function itself. And then if you are integrating separate functions, so a lot of times with polynomials, x squared plus 2x minus 4, like here is x squared, here's 2x, and then the other one, another third function would be minus 4. You can set up separate integrals for each one of those functions if you had to. But they do have to have the same limits. So a to b, a to b. They have to have the same limits in order to be able to do that. And then down here, evaluate that integral using each of the following values. So you're using these properties up here that we just learned to figure out what these integral parts would be. So see if you can go ahead and work on this one. And just to clarify, you're given this information and you're asked to integrate this. Go ahead and pause the video, try this, and come back. You can set up each individual integral like I did here. And then looking at this, you know the integral of x squared is 26 thirds, so the integral of negative x squared is going to be negative 26 thirds. The integral of x is 4, so the integral of 4x is going to be 4 times 4. The integral of the integral of just 1, for example, just 1 dx is 2, so then this is going to be 3 times 2 on that last one. And then when we go through and simplify all of those, you end up with 4 thirds, or 1 1/3. And it's a positive 4 thirds. We're not going to talk too much about this, the preservation of inequality. I'll show you a picture using an example. It's pretty, again, one of those things that just has to be said, right? So, you know, for example, on the first part, it basically says if you have a function that's always positive, so I'm going to draw a picture here. If you have a function that is always positive, so let's say this is my function. Okay, it's always positive. Let me do a linear function here. I can do better. Let me zoom in. Let's do this. Let's do like an x squared type. So this is always positive. The y values are always positive. So if I find the area from like any a to b, it doesn't matter. Whoops, b, a. What this says is that this area will always be greater than 0, right? That area will always be greater than or equal to 0 because it's above the x-axis. So that's what that first part says. And then the second part says if you have two functions, okay, so let's say we have two functions. Let's say one of them is 2x plus 4. So you have y equals 2x plus 4. And let's just say it looks like this. So here's this function. And then let's say our other function is y is equal to x plus 1. So here's 1. And then it's not going to be as steep of a slope. Now, you would agree that this function is higher than this function, right? It's above that function. So then that applies that the area of the higher function, which is the 2x plus 4, is going to be greater than the area of the lower function, which is x plus 1. And it just makes sense, right? So here's your higher function, and then here's the area of your lower function. Obviously, there's more red than purple. And so that's what this says. The inequality, meaning if this function is always greater and this function is always smaller, then the greater function is going to have a bigger area underneath those curves. All right, so that's really what you need to know for those inequalities. Don't worry about writing down those definitions. Maybe draw these graphs and write a little snippet to the side so you understand what you're looking at there. And I believe that is it for this video. I hope you enjoyed. Hopefully these pictures right here makes a little more sense. And in the next set of notes, we are going to look at the fundamental theorem of calculus, where we will be getting rid of the rectangles and finding the exact area under the curve using this extremely powerful tool called the integral. I'll get it. Hold on. Gotta wait. There it is. Until next time, folks.